Hi everyone. Today's lead code problem looks very simple at first glance, but it actually hides a really elegant bit manipulation trick. In this video, we will solve the problem step by step, optimize it properly, and by the end, you will understand a powerful technique that shows up a lot in interviews. The problem called prime number of set bits in binary representation. We are given two integers, left and right, and we need to return the count of numbers in that inclusive range, left and right, that having a prime number of set bits in their binary representation. What does that mean? For every number in that range between left and right, we need to convert that number to its binary representation. Then we count how many ones it has, and if that count is a prime number, we increment our answer. So basically, we have three steps. First, loop over the range, then count how many ones in each and every number, and finally, you check if that count of ones is a prime number or not. So let's take a quick example. Imagine that you have the number 10 in its decimal representation. So if we convert it to its binary representation, it's going to be 1010. Then we will count how many ones in its binary representation. In this case, it's going to be 2. Then we will check if that count is a prime number or not. And here 2 is a prime number, is prime. So we will add or increment our answer by 1. That's pretty straightforward. But the real question is, how do we do this efficiently? The most obvious solution is, for each number, we shift it bit by bit. Count the number of ones, then check if the count is a prime by dividing it by all the numbers from 1 to n. This works, but it's not optimal. We are doing unnecessary work again and again, especially in the prime checking part. But the first key observation here is that the range of the left and right is less than or equal 10 to the power 6. That means that the number of set bits or 1 of any integer in this problem is very small. Even if the number is large, the maximum number of set bits is around 20. And this is what we have in the first hint here. That means the only prime numbers we will ever care about are 2, 3, 5, 7, 11, 13, 17, or 19. So instead of recalculating prime numbers every time, we can just store them once and do a constant time lookup. Now let's move to the fun part, which is counting the set bits or the ones in the binary representation efficiently. There is a classic trick using this operation. If we have a number n and we end it with n minus 1, that will remove the lowest one from that number. Each time we apply it, the number of ones decreases by exactly 1. So instead of checking all the 32 bits, we loop only once per set bit. That makes the solution much faster and cleaner. So let's take an example. Again, our 10 number, if we end it with n minus 1, which is 9 in this case, its representation is 1, 0, 0, 1. That will result in 8. So we have eliminated the first or lowest one in that binary representation. And again, if we AND the 8 number with 7, that will eliminate the second one. Now, let's move to the code. First, we will store all valid prime counts in an ordered set. This lets us check primary number if the number is prime in a constant time. So I'll define an ordered set of integers. I'll call it primes. I'll set with all the valid prime numbers 2, 3, 5, 7, 11, 13, 17, and 19. Then I'll define a variable called answer to hold the final answer. Then I will loop over the range from left to right. We use less than or equal because it's inclusive range. And at that time, we will need a helper function to count how many ones in each number. So let's say I call variable bits, and I'll assign it the return of a function called count bits. So let's go and define a helper function, count bits. I initialize a variable count to 0. Then while the number n is not 0, because as we have seen in the example, the number after multiple ANDing with between n and n minus 1, it will end up to 0. And each time I'll increment my count variable. So here the variable bits will hold the number of ones. Then I need to check if that counts or bits exists in my set. And if so, I'll increment my answer. So let's run to check if there's any compilation error. Okay, all test cases passes. Let's submit it. And as you can see, the time complexity here is of n, where n is the size of the range, and the space complexity is O of 1. because the prime set is a constant size. This is about as efficient as it gets for this problem. So the big takeaways from this problem are: first, always look for constraints that limit your problem space. Then, pre-compute when possible. And finally, uh, learn bit manipulation tricks. They are extremely powerful. If you found this explanation helpful, don't forget to like the video, subscribe for more LeetCode daily challenges, and I'll see you in next one. Bye.